Good afternoon, everyone. Welcome to attend the second training course. Today's topic is visual slope stability analysis. Slope stability analysis is a very important portion of geotechnical engineering related to highways, railroads, airports, canals, and also minings, dams, landfill, and excavations. So we will discuss this today. The first, I will discuss the basic theories of slope stability analysis, then the different failure surfaces. The third part will relate to how to use visual slope for slope stability analysis. For the theories, I will go a little bit fast, and you can look at the detail from your soil mechanical boxes. First, all slope stability analysis now currently is based on limit plastic equilibrium theory, which is the slope is very close to fail, but still hold, still in a balanced condition. The way to do it, except the strength reduction method or the other methods, is first assume a failure surface, then calculate the shear stress along this failure surface and also the shear strength around this surface. The shear strength divided by shear stress result in factor of safety. If shear stress multiplied by a very small portion of the length, then we have a sliding force along this length, and the shear strength multiplied by this length results in resisting force. And if we add these shear force together, which is a sliding force, and the shear strength together, then result in a resisting force. Resisting force divided by sliding force is a factor of safety. The basic theory of slope stability analysis developed with different methods. The first very common way is the slice method, in which there's a Bishop method, Yanbu method, and the Spencer method, and the Morgenstorn-Price method. Those are most popular methods in slice method. And then is finite element methods. Besides that, due to the test result variance, the probabilistic method becomes more popular now. Visual slope are the only program can handle all these three different methods. Now we just go to how to use visual slope for slope stability analysis. Visual slope can provide circular failure surface, user-defined failure surface, translational failure surface, composite failure surface, and irregular failure surface. So let's first go through the circular failure surface. We will discuss different methods for failure surface and how do we calculate the seismic condition and drop and the rapid drawdown analysis. Also discuss slope stability analysis for staged construction. And the last we will discuss about risk assessment. Now, let's just open Visual Slope. Let's open a file. This is a soil slope. And when we do a circular failure surface, we need to first define the entrance area from this green point to this green point. So the circles will go from this area and going up and out from the exit zone. And we can do many of those and find the lowest factor of safety. Consider that is the most critical failure surface. So once we, since last time we already discussed how to do modeling. So today we just open a file, not actually do the modeling itself. If you did not see that, you can always go back to our website and see the recordings. And now let's first open slope stability page. And we need first to define the entrance zone. So we can click X1 and then you can click again. This point will drop to the surface of slope. And for X2, which is this point, you can drop it, click it, it will drop. And if the slope surface is close to vertical, it is very difficult to have a point fall onto a vertical slope surface. In that case, you can click the right button of the mouse and the point will move horizontally and hit the slope surface like that. It will hit the slope face from horizontal direction. And the same way for the exit area. You can have this. Once you define the entrance and exit zones, you need to also define how many surfaces you want to try. Let's just say 600. After you define all these conditions, you can click Analysis. Once it's complete, you can see the factor of safety from this panel. And when you click the button, and this failure surface will show. But you may ask, how would you know this is the most critical failure surface? Is there something be more critical than that? The way to find out is if the failure surface, the point is far away from the point you defined, which means you find the most critical failure surface. On the other hand, if you say this failure surface is like very close to this point, and which means it may go further, will have a more critical failure surface, then you should have moved this further away. Let us search in this way. The same thing for the up one. If it's very close to the point here, then you have to move this point further away, let it search further. The same thing for those. If it's close to this, you need to let it go a little bit away, let it search further. So this is the way you try to find the most critical failure surface. Also, because this one we use the Bishop method, and if you use a different method, say Yanbu method, and you may find that the factor safety is different because every method uses its own assumptions and the simplifications. So those will make the result different. So if you use Yanbu method, you will find uh, the factor safety is 1.5 instead of a 1.69. So it will be different. And once you finish that, if you need print a chart, you can choose one of those, and it will ask you, do you want to put a soil label? If you say no, then the report will show, and you can print it, and then you can save it into different format of file, and also you can print the data report, and this can also be saved or printed. Okay, these are the way you do the analysis. Now let's look at if we use finite element method. If you choose finite element method, when you run analysis, it will automatically develop a mesh and do a calculation. Once it's finished, you can see the factor of safety. This one is a 1.60. It's almost like between Bishop method and the Yanbu method. But these are pretty compatible with finite element method. Also, I want to mention, it's not like Yanbu method is always result in smaller factor of safety. It depends on the conditions. So use which one, it's your decision and also your experience. This is the slope stability analysis for circular failure. Now, I want to also give you some other things. Say if we want a failure surface past a certain point, which may be your interest. Say if you have a chronometer there and showing it's sliding from there, you want to see what's the factor safety for a failure surface passing that point. So what you can do is you can click at this point. So there's a point, and then you can use this fixed point as analyzing point. So once you do that, and you can. This is still from the element method. You will see the failure surface will pass this point. Actually, every failure surface will pass this point. So you can define a point and let it pass. Also, if you want to consider the seismic condition, you click seismic button and also give the peak acceleration, say 0.1 g in horizontal direction. And the vertical, you don't have to put in, but let's just say a small one, 0.002. And once you do that, and your analysis, it's complete, and it's, no, sorry, and then we have to redo different way. And you click it, and you see the factor safety actually is 1.25. It's a small amount because it's a seismic condition. Under seismic condition, the factor safety can be lower than usual. Sometimes you just need a 1.1 instead of 1.25 or 1.5 or these. So these basically describe how do you use visual slope for a circular failure. Okay, now we move forward and say if we want, we will have a failure surface, say something like this. It's a rock, but if you use a circular failure, it very obviously it's not reasonable. Most likely it will slide over this line. And how do we simulate that? And let's see. Still use visual slope, and let's open. So this is a rock slope. If we think the rock will slide over the top of this type of rock, how do we do that? So the first one is we still use slope stability, but in this case, instead of choosing circular, we choose user-defined. User-defined. And the user-defined actually allowed you to draw a failure surface, any type of shape, along any line, you can draw a failure surface. So what you do is you click X, and then you will see, you can type this number in too, but more easily, you can just click that. Then there's a button here, and you can click it. And the first one should be a little bit above the slope surface. So this is the first point. And the second point, say just here. And the third point, let's say here. The fourth point, let's say here. And we'll continue on. The last one should be also beyond the slope failure surface. So once you define this failure surface, and you can run a slope stability analysis. The program will automatically truncate the portion above the failure surfaces. So now we have factor of safety 2.15. Well, some people will say that the reason for that is even though you have a right failure surface, but usually along the joints of the rock, the stress is much lower than the rock itself. But if we do this, we still use the stress of rock, which gives us a very high factor of safety. So how do we simulate this, the rock joint? There are two ways. Let's just say one way is you just draw a line around, make it a weak zone, something like that. I'll read through to save time. You will see there's a layer. This layer, the material is different. It's weaker than the rock itself. So we can let the failure surface go around this weak zone. So what we can do the same thing as we did for the last time. We're still going to the user defined, and then we go from here. The first one point is here. Second around here, and third one is around here. And the fourth one is here. And you can go on. All right. The last one is always be a little bit above the ground surface. So you have this line. Once you finished, you you do analysis, and once you finish, it is 0.9 something. It really depends on the soil strength, the joint strength around this. If you give it very weak, it dropped from 2 to 0.9. If you give it a little bit stronger, then it could be 1 something. So it's really you need to make a decision how strong this joint would be. And this is just for one line, but you can also let the program search nearby this line. See, is there anything can be weaker? So what you can do is we say we want to make 300 searches, and the search width will be 3 meters, which is 1.5 meters above this line, 1.5 meters below this line. So let's do a search. So it's finished, and you will see the lowest is still the 0.996, but not necessary is the last line, the last failure surface. It could be somewhere there, but it will go something like that, and you can see the different ones. Some like this will be a little bit high, and something like that. But if you want to see all 300, and you can print it, you'll see search around this band, and you can find the line there. Okay, this is the way to simulate the joint of a rock. This is just one of the ways, and let's see the other ways. We close that, and we go back to the last one. Last one we did, we find that the factor of safety is 2 something. Just confirm that it is about 2 something. But instead of draw a weak band, and you can actually do stress reduction directly from this panel. And let's say we reduce the friction to say 70% of the original one, and the collision we let it drop to 0.6 which is 60% of the original one. And then you run analysis, and you will see, oh, now it's almost like 1.4 something. The same way, if it's still too big and you think it may be only like half of that, you can click like 50%. You run analysis again, and it's still this much, not to change it too much. And anyway, you can do whatever reduction you want it. But also you can do a search, say 300, and would give 3 meters, and we do analysis, which may give you something, oh, which is much smaller. Okay, now this one is only 1.192, and the other one is 1.19. So these are the search. Maybe these are more smooth than what we had was pretty angular. So these will result in even a smaller factor of safety. So that's 2 different ways to simulate the rock joints. One is you just draw a bend. The second is you can use the strength reduction from this panel and for the analysis. In my opinion, this is a lot easier than the other one. So this is how to use visual slope to perform slope stability analysis for rock slopes. Now, the next one I will introduce to you is how to use visual slope to perform a composite failure surface. A composite failure surface usually is used between an interface, such as like you have a soil on the top of a rock. The soil will slide over the top of rock. You can use the so-called composite, which is in the soil area, the failure surface is circular. The ones that hit the top of the rock, it will just follow the rock surface. And this is the one thing you can do. Also, I will give example for the like a landfill or something, so you can see how this the composite failure surface can be used for some projects. So let's open one. This is the one we actually developed last time when we discussed about the modeling using tracing method. Now, the yellow top is actually clay, and the blue part is shell. And we try to simulate the clay layer sliding over the top of shell. So what we can do is just like we do a circular failure and give entrance zone and exit zone. But from here, there will be a circular here. And once they come out, it will be a circle. But once it hit the rock, it will go following the top of the rock. So what we need to do here is to go to modeling and use the limit line. So this is limit. Click this and follow the top rock. So this is the line we will draw. And then we go into slope stability analysis. And instead of choose circular, we choose composite shape. So once we choose that, and we already defined entry zone and exit zone, and we say we need around 500 failure surface to see what can happen. So we do analysis, and you find the effective safety is 0.84. So this you will see here. It's a circular, but to follow here, it will follow this rock, top of rock. And you can see the different ones, something like that. They will all once some portion is circular, but the ones hit, it will follow the rock. And you can see more. This is the composite failure surface, which you can use for some slope that has soil and rock interface. So this is the another way. And also that I give one more example of that. If I can find one. Composite 2. That's not the one I want. That's also the soil and the rock. I want to do a different one. Okay, this is a different one. This is a landfill project. These are solid waste, ash, and here is the liner, clay liner. On top of a clay liner, there's a geomembrane liner, and the landfill just to worry about the solid waste will slide over it and come out. So we use the interface is between the clay liner is with the solid waste and geomembrane liner. So we put a limit line along here, and we give entrance and exit zone. So we do analysis. We will see the failure surface is something like that. So you will see this is the way you can do for landfill 2. These the application of composite failure surface for our projects. The last one I will briefly mention about random failure surface. In some case that could happen. I just still bring the regular failure slope, and it's similar to circular, but when you can pick up irregular shape. So once you do this, you click, and it will have this one actually is 1.5 something. The shape is irregular. It's a random shape. You can see this one is like that. This one is like this. So these are the way you do a random shape failure surface. So just to get a summary, visual slope allowed you to do the different failure surface, include circular, user-defined, which is always be any shape, which means, and then the composite. After composite, you have a random failure. Now, the last thing we will discuss is the risk assessment. Because in many cases, once you run a soil test with a big project, you have run many soil tests for a section. And the soil test result may almost always not be just a one number. It will scatter around. And how do you use those numbers? If it varies a lot, how reliable your slope stability will be. For example, just this one. If the collision and friction angle varies quite a bit, and how reliable your slope stability will be. So let's take a look at the material part. Say fill here. We have collision is 30 kilonewton per square meter, and friction is 18 degrees. To describe the consistent of the soil data, we use a parameter which called the coefficient of variance. We can put the coefficient of variance into this for collision, and the coefficient of variance here for friction. And the coefficient of variance, the definition you can check on the statistical book. What that is? If it's a very small, that means the soil test is where the results are very close to each other. It's very close to their average number, but it's bigger than which means it's a wide scatter. So this is the number you will input to evaluate the input data, quality of the input data. Now, based on these, visual slope will let you to make a risk assessment. Say, if we say this is the original one, and we want to do a circular, and to do a risk assessment, we can just click on risk assessment and then click analysis. Once it's complete, you will see this is the value for the from the mean value, and this is the lowest possibility, and this is the highest possibility. But this one tells you the failure, the chance of failure is 2.24%. So that means if there's a slight chance it will fail. But if you increase the variance, then most likely this will increase. Let's just check if that is the case. So this is a clip. Say, let's go soil clay, and now it's 0.3. Let's say we have 0.4, and this is 0.3, and we'll close that, and close that, and then we run analysis again, and we still check for risk assessment, and once it's complete, now it's increased. It's like before was 2 point something. This is a 4 point something. It's still lower. The reason is the original failure factor of safety is pretty high. If you make this one a little bit different, say if I want to take this piece away, take this piece away, take this piece away, I run a slope stability analysis. Here. Oh, I don't want to run that. Oh, that is almost failed already. Oh, there's should not reduce that. So we'll do this way and run that again. See, now the fact safety is 1.2 something, and the lowest can be 0.8, highest can be 1.7, and the potential of failing is 22%, almost 23%. So it's a very high. So if the original you have used the mean give you 1.277, almost 1.3, you think the fact safety is enough. However, if the soil data is not that consistent, it still give you a very high chance the slope will fail. So you need to check that too. So this is how to use a visual slope to perform a risk assessment. So to this point, we almost discussed everything from how do you use visual slope to perform slope stability analysis, including risk assessment. So now, if you have any questions, you can always ask. And if you have a question, you can just turn on your microphone and you can ask. Well, not a problem. You can always, if you have questions, you can always send an email to us, and we can answer your question from there. And as I mentioned last time, the input file is very small, and you can always, we hope you always send your input file with your email, so we know what you actually doing, and we can open it, and we will respond very quickly, usually within 24 hours. But thank you so much for attending this training. And the next one will be stabilize an unstable failing slope, mainly discuss about soil nails and the retaining piles. In the soil nails, we just add a facing design function into it. Hope you can attend. Again, thank you so much. Bye.